Hi guys, welcome back to a new unit. This is Unit 3. Here we'll be tying in a lot of different concepts we've covered in the first 3 units so far in Algebra 2. I would say that this is one of the main or the biggest units, just because I think things start to make a lot of sense to students. All that we've learned so far seems separate. It all comes together here. So where we're going to start today is by looking at what's called the Remainder Theorem, and then we're going to look at solving by factoring with higher power. So these are things that we've talked about before in some way. We've talked about remainders of problems before. We've talked about factoring before. We'll look at them in a new context, and this will allow us to join together a couple of different things that we've discussed so far. The remainder theorem is a specific way to find just the remainder of a division problem, or something that might be constructed as a division problem. Now, you've had long division so far, and you've had exposure to synthetic division so far. The remainder theorem is a bit shorter, and the nice thing about it is that it allows you to determine what your remainder is without having to do a lot of different work. And the reason that we would want to know that is because if our remainder is 0, then we know 2 things straight away. Number 1, that whatever we're dividing by is going to be a factor of our problem. Think of how 18 divided by 2 is 9 without a remainder. The remainder is 0. Therefore, what does that mean? 2 and 9 are factors of 18. Same thing with polynomials, as we'll see. And the other thing is that as we're using the remainder theorem, we're going to be substituting a number into our numerator or our dividend, the thing that we're dividing from. And if that number turns everything into 0, then the remainder is 0, and that number that we plug in will turn out to be a root 0 or solution to our problem. Now, while that is very good, we can only use the remainder theorem if we can also use synthetic division. So you have 2 different methods basically to find your remainders here. Synthetic division is one, which we will come back to in a later topic. And the remainder theorem itself can only be used if the thing that you're dividing by, your divisor, has a lead coefficient of 1 and a degree of 1. So something like x plus something or x minus something, not 3x plus something or negative x or x squared. You can't divide by those things and still use the remainder theorem. But when you can use the remainder theorem, there are 2 basic steps, and those are listed here. We're going to set our divisor equal to 0 and solve for x. This is something similar that happens in synthetic division. Okay. What we're going to do after that is take whatever number that we find there and plug it into our numerator or our dividend, the thing that we're dividing from. That will actually tell us what is the remainder for our problem. So an example of this might be if we're trying to decide if x minus 3 is a factor of this function. Now, the way that we could do that is to try to factor this, and we won't know how to do that until next video, so I can't do that. We could try to divide this from this, and we could use long division, right, or synthetic division. Okay. And if the remainder was 0, then yes, it would be a factor. It would divide evenly. That's what we want to see. Does this divide evenly? But the remainder theorem is going to be shorter than both of those methods. And the remainder theorem says, once again, we take the thing that we would divide by, in this case, our divisor is x minus 3. Set that equal to 0 and solve. X equals 3 in this case. This is the number that we're going to use to plug into all of our variables to our numerator or the function that we would be dividing from here. Okay, so replace all your variables with a 3, see what you get. In this case, that's not 2x to the 4th anymore, it's 2 times 3 to the 4th power. And 3 to the 3rd power. Negative 4 times 3 plus 8. I would use a calculator to simplify this. Remember, PEMDAS, exponents come first. Don't multiply 2 times 3 first. Take 3 to the 4th power first. So simplify with your exponent first, you get 81. Simplify this expression. 27 minus 12 plus 8. Okay. And if you do simplify that all the way, what you'll end up with is that the remainder, the number that you find here, is 23. You have 23 units left over. If you were going to divide this by this using synthetic or long division, you would get the same answer, a remainder of 23. And remember, the way that we write that would be 23 over x minus 3. So what does that tell us? Did this divide evenly? And the answer would be no. We had a remainder left over of 23. So the question was, is x minus 3 a factor of this? No, doesn't divide evenly. It's not a factor. Is 3 a root 0 or solution for this? No, it didn't turn our remainder into 0. It turned it into 23. That would be how we would approach one remainder theorem problem. Another way that we could express the same sort of question is, what's the remainder when we try to divide this function by this binomial, right? X plus 8, two terms there, that binomial. So once again, take the thing that you would be dividing by, in this case, x plus 8, set that equal to 0 to solve for x, so subtract 8 to both sides. And we see that the number that we're really going to be using here is not positive 8, but negative 8. Negative 8 is the number that we're going to try to substitute into our function and see if our remainder is 0 or not. So if I replace all my variables with a negative 8, this would be step 2. I'll get negative 8 squared plus 9 times negative 8 plus 8. All I've done there is replace my variables with negative 8. Simplify that a little bit. Negative 8 times itself, a negative times a negative is positive 64. 9 times negative 8 is negative 72, plus 8 off to the side. Aha! This does equal 0. So, is x plus 8 a factor of f of x? Yes, it is, because it divides, or it would divide evenly from it, as the remainder theorem proves. This 0 is your remainder. And because it's the remainder, okay, is negative 8 a root 0 or a solution to our problem? Yes, it is. Okay, that negative 8, by the way, would show up on a graph. And be one of our roots, zeros, or solutions. We would have another one, but we only wanted to find out if this was one of them. Yes, negative 8 turned everything into 0. Okay. So the remainder theorem, division, factors, right? If we factored this problem, we would end up with one parentheses being x plus 8. All of these things are tied together. Okay. Division shows us, is this a factor? Factoring would be another method to show, is this a factor? Yes, it is in both cases. The remainder is 0 when you divide. The result is 0 when you plug in negative 8. The way that you would find that is by setting your divisor equal to 0 and solving. That is the remainder theorem. That helps you answer a lot of different questions and tie in things like factoring, division, the remainder theorem, finding remainders, graphs. All of these things start to come together in this unit like we have just seen. One other thing that I wanted to cover today that sort of touches on what we just talked about is factoring. Okay? Because we've factored before, and we've had two different types of factoring problems with binomials and trinomials, 2 terms versus 3 terms. I wanted to go over those again, but give a little bit of a different spin on it, because today we're going to look at factoring with higher powers, so things that not just involve x squared, but that was our quadratics unit. Quadratic expressions all have a degree of 2. Higher powers would be something that have degrees or exponents more than 2. So in this case, to remind us of the pattern that we've seen in the past when we're working with perfect squares, right? When we're subtracting perfect squares, it's always going to end up being something plus something times something minus something. So for example, x squared minus 1 ends up being x plus 1 times x minus 1, because the square root of x squared is x. The square root of 1 is 1. Those are the numbers that go in to our pattern on the left and right side of our symbols. The square root of x squared is x. That came from the left of our symbol here. So they go in on the left side of our parentheses. Square root of 4 is 2. So 2 goes on the right side of our parentheses. This is always our pattern. And the only real difference with higher powers, okay, I've written out a new pattern. Hopefully you should be able to see that down here, all we're doing is thinking about what times what equals these first terms. We're still square rooting, oops. We're still square rooting both terms. The square root of 4 is still 2. We still have something plus something times something minus something. The only difference here is that since we have higher powers, we do need to take into consideration what goes in on the left side of these parentheses. Well, we have to think about what times what is x to the 4th. And that'd be x squared times x squared, because 2 plus 2 is 4. What times what is x to the 6th? X cubed times x cubed, because 3 plus 3 is 6. What times what is x to the 8th? X to the 4th times x to the 4th. It's very similar to the pattern we've shown earlier, where we had x plus 2 times x minus 2. We're just increasing our exponents, right, by square rooting our first terms. The square root of x to the 4th, what times what is that? X squared times itself. Okay. And that would be our perfect square factoring pattern applied with higher powers. Not very different. Only difference here really is that we're working with higher powers in our factorizations as well as our original expressions. For trinomial factoring, very similar. Okay. Now for both perfect square factoring and trinomial factoring, you can use the box method to help you to factor. Right? We've talked about that in the past, where if we're given an expression, we're asked to factor it or break it down. Okay. We're ending up with two parentheses, and the way in which to find that with the box method is to think about, for example, what times what is x squared? Remember, whatever these factors are had better multiply back out to equal your original problem. So something times something had better equal x squared. In this case, we know it would be x times x. That would show up as part of our answer. Likewise, something times something had better equal -6. Now we have a few options here, right? Factors of -6 could include things like 1 times, or 1 minus -6, sorry, 1 times -6. -1 times +6 would also equal -6. 2 times -3, or -2 times +3. All those things, all those pairs multiply to give the same number, but only one of them adds to give -x, right, when they're combined. And the way that you see that is by asking, what plus something or what minus something equals -1 here? Does 1 minus 6 equal -1? No. Does -1 plus 6 equal -1? No. 2 minus 3? Aha, that does equal -1. 3 minus 2 does not. That is the list of pairs I'm going to use, because as we see here, if we do choose these numbers, x times -2 is -2x. X times 3 is 3x. And yes, these do, oops, should be reversed, excuse me. -3 and +2. 2 minus 3, 2x minus 3x. Yes, that gives us -1x. Those terms had better combined. So you saw that I had the signs incorrect there for a minute. You have to make sure that your signs are correct so that when you simplify, 2x minus 3x, yes, that equals your original problem. That is how we factored in the past. And how we're going to factor with higher powers here is no different, right? It's not really any different. The main difference, in fact, the only difference, will be that because our powers are higher, we need to, instead of looking for x squared, look for x to the 4th. What times what is that? X squared times x squared. We're still looking for -6, so we still look for the same factors here. Again, only difference will be that instead of +2x and -3x, there'll be +2x squared and -3x squared, because you're multiplying by x squareds now, which is good because that's what our middle term has. So in this case, not much change. Once again, we still have a +2 and a -3. But in this case, you'll notice that When we factored with higher powers, we ended with factorizations that had higher powers as well. And that takes us into our final topic for today. And that is going to be solving by factoring. So we've seen how to factor with higher powers, not very different from what we've seen before in the past. Okay. But how do we solve or find roots, zeros, or solutions to our factorizations? Okay. Remember, when we're looking for roots, zeros, or solutions, we did this in one of our first couple units. We're setting everything equal to 0. We're trying to see where on the graph does y equal 0, if at all. So in this case, we've talked already about how x to the 4th minus 4 is x squared plus 2 times x squared minus 2. This is our perfect square factoring pattern that we saw earlier. Okay. If you multiply this back out, it gives you the same thing you started with because some things will cancel. We're trying to find solutions, so we're going to set each of those parentheses equal to 0 and solve just like we've done in the past. And in this case, here's something else that comes back into play, the root method. We've talked about the root method before as one method of solving. That's going to be what we use when we're solving by factoring. Opposite operations to get x by itself. So at some point you'll need to square root both sides. Don't forget that a plus and minus symbol then show up, right? And in this case, x will equal plus and minus I squared root of 2. Imaginary numbers comes back up here. Everything that we've had for the first 3 units comes together in Unit 3. Imaginary numbers, all the different types of solving methods that we've done. The quadratic formula will show up again. Okay. Factors, factorizations, division, remainders, all of this comes together here very beautifully. Okay. For the other parentheses, add by 2 to both sides. Again, you'll have to square root both sides. In this case, however, you'll notice we don't have I show up as an answer. Instead, it's just plus minus positive square root of 2. Now, what I will mention, I'm going to basically end the video here with a teaser for what we're going to talk about next, is that when we've solved in the past, we've ended up with things that have 2 solutions sometimes maybe, or 1 real solution, or 2 complex solutions. We haven't ended with any more than that. But what you should see here is that we've ended with more than 2 solutions. Right? How many solutions have we ended up with? We ended up with positive I squared root of 2, negative I squared root of 2, positive square root of 2, and negative square root of 2. We ended up with 4 solutions. Think about what our degree was for our original problem. It was a 4. And how many solutions did we end up with? 4. Your degree will always tell you how many solutions, roots, or zeros you have to a given expression or equation. That is something that's called the Fundamental Theorem of Algebra. It's very, very important for Algebra 2. That's where we're going to pick up with our next video, and I hope to see you then.